so our lesson today, Pre-Calculus 20, we're on section 7.2. We're talking about absolute value functions. Now, we've talked about absolute value in the past. Guys, no fooling around your calculators, okay? No writing messages, no goofing around. Focus on what we're doing. You get to use those graphing calculators to graph functions a little bit later, okay? So you don't need those right now. Absolute value functions, okay? We've talked about absolute value of numbers, right? If you have an absolute value of a negative number, that's the same as just the positive version of that, right? So that the absolute value signs kind of get rid of negatives, so to speak. So if we're talking about absolute value functions, what we're talking about is, I don't know if you can see this in your textbook, but y equals the absolute value of f of x. So that would be like y equals absolute value of x, or y equals the absolute value of 2x plus 1, or something like that. So you have a function with absolute value signs on either side, okay? Now, how does that differ from regular functions? We're going to explore that today. So the first thing we're going to do is we're going to take a look at this chart right here. And I want you to copy this chart out. So make 3 columns real quick. You're going to have an x column, and you're going to have an f of x column. This is the same as y, right? And then you're going to have a g of x column. So just make three columns. Here's the x values are -3, -2, -1, and then 0, 1, 2, 3. So take a moment just to copy that out, and we're going to sketch the 2 graphs on the coordinate plane when you're done. All right, so hopefully you've had a chance to copy this down. Now what we're looking at, the x value and the y value here, for each x value, the y value is the same number. So this is actually y, or f of x, let's say. F of x, that's what's shown, is equal to y, okay? Or y equals x. So this is the y, and this is the x. So they're the same. So we know what that one looks like, right? Let's do that in blue. So some of these points here, -3, -3. So 1, 2, 3, 1, 2, 3. That's this point right here. -2, -2 is this point right here. -1, -1. 0, 0, 1, 1, 2, 2, 3, 3. Okay? So those points make up this line right here. So this is your y equals x line, right? Y equals x. So if we had y equals absolute value of x, then on the chart here, this y value, we would apply the absolute value sign to it, right? So it actually equals +3. And this -2, if we apply the absolute value, that equals +2. This one equals +1. The absolute value of 0 is still 0. Absolute value of +1 is still +1. And then we have 2 and 3. So if we graph this one, if x is -3, then y for the absolute value is +3. So we go 1, 2, 3, and then up 1, 2, 3. -2 and +2. -1, +1. 0 doesn't change, so we have 0, 0 being the same. And then 1, 1 is the same, 2, 2 is the same, 3, 3 is the same. So what you see happening here is the absolute value function looks like this. It's a V, really. And notice on the positive side of the x-axis there, for the positive values of x, it's exactly the same as y equals x. Okay? So that's the simplest absolute value function that we're going to study. That's the simplest one. What can we take from that? Well, what you want to understand, what you want to realize is that any y values that are negative, like this is -1, -2, -3. So these negative y values, if you have an absolute value, right, then then it's whatever is negative on the y has to get flipped. Okay, so for example, if we have a -2 for the regular y, the absolute value is +2. So this -2 gets flipped. It's like it gets reflected. Okay, but only for the negative. So where it normally be negative, it gets reflected. Okay. All right, let's take a look at this one. Now, maybe you don't have to copy this one down. Okay, so just watch, because I'm just going to go through this a little quicker. And so if we have y equals f of x, and then if h of x is the absolute value, okay? So that this is negative 3, 6, so this would be, this 6 becomes, well, 6. That 1 is 1. Negative 2 is positive 2, positive 3. Okay, so everything is the positive version. All right, so real quickly, let's plot the f of x. Let's do that in red. So if we quickly plot those points, that looks like a parabola, doesn't it? And I think if we filled in all the points in between, we would have something that looks a lot like a parabola here. Apologize for my messiness here. Okay, so this would be a parabola. All right, so h of x is going to be the absolute value of f of x. Okay, that's what h of x is. So wherever there was negative values here, so these three, right? This one, and this one, those are now positive. Everything else is the same, so this is the same, that's the same. This one, though, is a reflection. So it's actually, instead of going 2 down, we go 2 up. Right? Oh, come on. This one, instead of going from the origin 3 down, we go 3 up. Instead of going 2 down over here, we go 2 up. And then all the positive ones would still be the same. So the blue graph, I'm going to do h of x, which is the absolute value of this one. In blue, it looks like this. All of these values will be positive, and they'll stay positive until you hit 0. Then the values get reflected. So they kind of come up, and they're a reflection of what was down in the negative part there. So it goes like this, and then comes up. All right? So that looks a little funny, doesn't it? Kind of looks a little funny. But anything that's below the x-axis, if the whole thing is absolute value, then anything that would be originally negative has to get changed to positive. So that's if the whole function is absolute value. That's what happens. All the negatives get turned into positives. So this is what this blue one looks like without the red there. That's what it looks like. Okay? Kind of funny, hey? But this is where it was before, but it gets literally folded at the x-axis and flipped up. Everything gets folded and flipped right up. Now, another way to look at this, though, and this is kind of the important part, maybe the little tricky part, so I'm trying to lead up to this, but the important part is that you need to be able to see this as two functions, two different functions. So one function, if I were to outline this in black, would be the regular parabola that looks like this, right? That looks like this, the one that we had at the beginning. That's the one, all right? The second one, if I were to do this in a different color, like let's do it in red. So then the second one is this parabola that faces downward, you see? So there's actually two parabolas. We're taking pieces of two functions. That's why it's called a piecewise function. Actually, I think instead of just writing it out there, I think I've got the definition here for you. Okay, I've got it all here. So let's focus on this little slide here. All right. So an absolute value function. Okay, we know about an absolute value function. It involves the absolute value of a variable, or the absolute value of the f of x. And now this piecewise function, which you should jot this down in your notes, okay, as much of this as you can. The piecewise function is a function that's composed, maybe I'll zoom in for you. A piecewise function is a function composed of two or more separate functions or pieces, each with its own specific domain. They combine to define the overall function. Okay? And that's what we want to focus on here in this next few minutes. So to explain that a little bit further, the absolute function, or sorry, the absolute value function y equals absolute value of x can be defined as a piecewise function looking something like this. So remember, here's the graph up here. The absolute value, which is this one right here, that's the absolute value function. It's overlapped a little bit, but that in blue, that's the absolute value function. So that function looks exactly like f of x when all those y values are greater than or equal to 0. This right here, in red, is talking about this part right here. It's saying that the absolute value function is the same as the function without any absolute values if f of x is positive. So if f of x is positive, they're the same y values, right? That's what we just learned. And this is the tricky part. If f of x is negative, and let's do this in black maybe, if f of x is negative, like this, then it's the same as the negative version of that. You would basically take the original function and multiply it by a -1, which is sort of the actual algebraic representation of flipping. Okay, so if we flip the y values, we basically multiply all of these values by -1, and this flips up to here. This flips up to there. The value, the sign changes. Okay, so the black part is this. Notice if we continued on with this black line, it would look like this, right? And that's y equals -x. That's what that is. So for the absolute value, y equals -x for part of the graph. This red one looks like y equals +x. So the absolute value function looks like y equals +x for part of the graph. So that's where we have pieces. And I know this is the first time you've seen this. This could be really confusing. But if we go back to this other one, so I'm just going to jump back. Maybe this is easier to see. For part of the graph, it looks like the positive parabola that's facing up. Okay, so we take a piece of that graph, and then the other piece of the graph looks like the separate negative opening down parabola. And we take pieces of each of those. Okay, and so when we do that, the final picture looks like this. This is, and this over here are part of the positive one, and then this middle part is part of the negative one. Okay? The piecewise is possibly the trickiest part. Okay. Any questions? All right, so I've got y equals x plus b, which when b is 0, it's the same as y equals x, right? So if I change b with this slider, the b is the y-intercept. So if I make b larger, this line sort of slides up, right? This b is 1.7. Guess what? The x-intercept is 1.7. If b is 2.5, the x-intercept is 2.5. Okay, we got that, right? We know about that. So let's go back to here and let's make this 0 again. The absolute value, y equals absolute value of x, is just what we graphed before. This is just what we graphed before. If I move this slider, let's say I move it left and I bring the intercept down a little bit, okay? All of this portion of the graph is below the x-axis, right? All of these have negative, look at that, negative 0.56. They all have negative y values. Do you see that? So if I make the absolute value of this function, all of these y values are going to be the same. 0 will be the same. But what should happen to these negative y values? What should happen to those? Are they going to stay the same? All of these y values should be, the negative version of themselves. So they're going to flip to above the x-axis. So if I light this one up, everything that's below here cannot be negative anymore. It has to be the positive version. So you get this V happening again. Okay? And if I move this slider around, so I bring it back up to 0, look where the reflection is. It's at 0. Over here, these values are all positive. That's all good. But anything that's negative has to literally flip up here. So it folds on the x-axis. Okay? Okay, so I'm going to get you guys to do this now. why don't you graph y equals, on your graphing calculators, graph y equals, and this is kind of what your graphing calculator looks like right here. So go to y equals, okay, everybody paying attention? Hey, wakey, wakey. Y equals x squared minus 3. Okay? Graph that. X squared minus 3. I'm going to graph it up here as well. X squared minus 3. And what I want you to do is I want you also to graph y equals the absolute value of x squared minus 3. And I'm going to get you to look around and see if you can find the absolute value signs. I'm going to give you a few seconds to do that. Some of you may know where that is, but I'll show you in a second. All right, you hit the math button and you go over 1, and you see this ABS. That's the absolute value function. So absolute value, oh, whoops. I guess I have to do this over again. Say minus 3. So math over to number, absolute value, and then you do your x squared minus 3. It says error. Okay, well, here's mine. Now it's tough to see both of those in there, but this is the exact pair of graphs that we graphed earlier in the class. You see that? So let's go back to our notes here. This one right here. See that? That's okay. So that's kind of what we were looking at there. Now on Desmos, it might be a little bit easier to see. Look at this. So here's y equals x squared. Let's say minus 3 right there. X squared minus 3. And this is the absolute value of x squared minus 3. So it's the same over here. It's different here. Okay? Now if I move that 3, x squared minus 4, look what happens. See? Now if everything is above the x-axis, if all the y values are positive, there's no change. You see how they're both the exact same graphs. But as soon as it dips below the x-axis, as soon as those y values become negative, the absolute value part takes over and it flips them. Okay? So see, if they're all positive, it's the exact same graphs. Okay, so in this, what I just set z to a variable, so I can change the value of z. So here's z equals 3. So this is x squared minus 3. But if I change x squared minus 4, that's what it looks like. Okay? Okay? All right. And so you can do absolute, and I would encourage you guys. Okay, so I will say this. Use Desmos to confirm some stuff. Use your graphing calculator if you want to graph some stuff. But you're supposed to be doing this without a graphing calculator. You're supposed to be able to identify and to sketch this without a graphing calculator. And so in your notebook here, where is it? Or in your textbook, I should say. In your textbook, some of the questions say, graph this, okay? So consider this, for example, and graph it. So let's go over example 1 and as we conclude our lesson here. So write this down in your textbook or your notebook, please. Copy this question down here. Okay, I'll give you a moment to do that. All right, so with this equation here, absolute value of 2x minus 3, what you should notice right away is that y equals 2x minus 3 is a straight line. Right? Is that good? Thank you. Y equals 2x minus 3 is a straight line. It's a straight line with negative 3 as an intercept. What else do we know about this line? It has a what? We have an intercept of negative 3. It has a what? What else? Y-intercept is negative 3. This is probably the most obvious thing, guys. Remember, this is y equals mx plus b. Remember that? B, y-intercept, what's m? M is the slope. So we know the slope is 2. Okay, that's what I was looking for, but x-intercept is another fine thing to do. If you let y equals 0 and you solve for x, right, that's going to give you the x-intercept. So it's going to be 3 equals 2x, x equals 3 over 2. So where's 3 over 2? Well, that's 1.5. So there's going to be an intercept. So the slope would be easier to sketch the line, use the slope. Up 2 over 1. Up 2 over 1. Up 2 over 1. You'll see that it will coincide with this intercept that you've determined. But that's what this line looks like. Okay? All right, now we've graphed this line right away, and we know how to get this from the graph. So let's pretend that we didn't do that, because you kind of have an idea now what this absolute value is going to look like, right? So they're going to be functions are going to be a little more complicated than this, but determine the y-intercept and the x-intercept. Okay, we just did that. Sketch the graph, we did that. Domain and range. Okay, so what we have to think about here is, are there any restrictions on the x? Because that's what's going to determine the domain, right? So are there any values for x that are not allowed? Remember, this is absolute value. It's not a square root, so we can have a negative under here. That's fine. So it can be negative. The thing is that, you know, does any value of x cause this to have a denominator that's 0 or a negative under a square root or anything like that? No. So the domain, any value for x is okay. So for the domain, x can be any real number. The range, though, okay, the range is the y values. So what about the y values? Well, if you take a look at the graph, right, the range would be sort of where on the axis that the graph can be. And so if we take a look at the actual graph of this one, I'll do this in red, all of these points from 0 and above are the same, but these points are reflected, right? So this is what the absolute value actually looks like, this function. So if this is entirely in the absolute value, if the absolute value signs are encompassing the whole function, then the range has to be greater than or equal to 0, because nothing can cross this 0 line. So the range is greater than, y greater than or equal to 0. Does that make sense? Because it can't be below. All right, expresses a piecewise function. So this might be the toughest part. I'm not really sure. Sorry, D. So piecewise function. You know that y equals, and we're going to have to make these little funny brackets here, the braces, because you're going to have 2 sections. One section above, one section below. Okay? So in doing the piecewise, hope you're following along here. Okay? Doing the piecewise, you have to have what part of the graph looks like in part of the domain, and then what the other part of the graph looks like in the other domain. So we got to separate it. And it shouldn't be too hard to see from all the work we've done so far that this line right here is one of the pieces of this. So what is that? Y equals 2x minus 3. That's what this blue line looks like, right? The blue. Y equals 2x minus 3. See that? So part of it is 2x minus 3. Let's talk about the domain in a second. What about this red one? Part of it is this red line. So what is this red line here? If we continue this on, what is the equation of this red line? Well, we can figure that out. What's the intercept? It's positive 3. And what's the slope? It's down 2 over 1. So it's negative 2x plus 3. Okay? So that line forms the other piece. Negative 2x plus 3. Okay? So The shortcut really to this is that the other piece is y equals the negative of the original one. See that? That's the negative of the original one. Because, look at this. F of x, it looks like the regular function, and it looks like the negative version of that function for the other piece. So that's kind of a shortcut. All right, now for what domain? Okay, so for what domain? This should be for the x values, but let me just see. Yeah. So 2x minus 3, that actually is the piece of the puzzle for everything that's beyond this x value. So that's why the y-intercept is important. Okay, this is really important. So the domain for this part is when the x values are greater than or equal to what? What's this x value here? It's the intercept. So we found the intercept to be 3 over 2. So when x is greater than or equal to 3 over 2, that's when this absolute value graph looks like this function. That's this part. Okay? And then the absolute value graph looks like this one in red when x is less than that intercept. So when x is less than positive 3 over 2. Okay? So this section is all about this example, really. There's a little bit more to it. We're gonna another example would be where we use parabolas. Okay, so that's an extension, and that's going to be example 2. I'm not going to go over that in this lesson. Okay, because I want to give you some time to work through this on your own. But you can also look at example. Yeah, I guess it's example 2 in the text. All right. So there's example 1. I guess I will make mention of one more just definition. Have you guys ever heard of invariant point before? Invariant point? No? Okay. So let's talk about invariant point real quick. The point, or the points that remain unchanged when you have some kind of transformation, like an absolute value transformation, the point or points that remain unchanged are called invariant points. Variant means it changes. Invariant means it doesn't change. So we have a lot of invariant points, don't we, on this graph? The original graph and then the absolute value function graph. So that's what an invariant point is. Okay, so please take a moment to read through the key ideas, and I'll give you your assignment. Here's your assignment for 7.2. Please copy that down. Did you copy this down?